So standard feature transforms. Okay, and there are many standard feature transforms: polynomial transforms, sinusoidal, i.e. Fourier transforms, radial basis function transforms, and so on and so on. There are lots of different kinds of transforms. Okay, but you just need one, okay, that can be your go-to feature transform when you don't want to spend too much effort. You've already spent effort collecting the features, now you just need a little more power. Okay, and so what's the standard polynomial feature transform? So the polynomial feature transform. Okay, so let me illustrate it in 2 dimensions. So you have, your original input vector 1, x1, x2. Think of this as the original input vector in 2 dimensions. So I'm illustrating in 2 dimensions. Okay, so the polynomial feature transform of degree 1 is just to take your input and transform it. So degree 1, okay, is to take so let's call that phi 1, is to just take your input and transform it to what it was. I don't need a transform to do it. I'm just showing you that, this is the polynomial of order 1. So you have your 1, the augmented 1, and your 2 terms that you had before. Okay, what about the degree 2? So this is the degree 1. Degree 2, phi 2. Okay, you got your augmented 1. Now what you're going to do is you're going to have your linear terms, x1, x2, and you're going to have all the quadratic terms. That's why we call it the degree 2. Okay, so basically all monomials that involve your original dimensions of degree at most 2. That gives us the degree 2 polynomial transform. So we're going to have x1 squared, x1, x2, x2 squared. Okay, and so this is degree 2. Okay, and let's see. So here d tilde is 2, is the same. So the VC dimension is 2. D tilde, dVC tilde is 3. dVC tilde is 6. Okay, and now let's look at phi 3. Okay, so that takes my original input and construct 1, the linear terms, x1, x2, the quadratic terms, x1 squared, x1, x2, x2 squared, and the cubic terms, x1 cubed, x1 squared, x2, x1, x2 squared, x2 cubed. Okay, so this is the degree 3 polynomial transform for the 2-dimensional original input. And you see that, what we have now is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9-dimensional space, and the dVC is 10. dVC tilde is 10. And if you want, you can go ahead and compute phi 4. Okay, and this is 1, the linear terms, x1, x2. Okay, the quadratic terms, x1 squared, x1, x2, and so on, up to x2 squared. And then you'll have the cubic terms, x1 cubed, and so on, up to x2 cubed, and then x1 to the 4th, and so on, up to x2 to the 4th. Okay? And so here you're going to have, how many additional terms? You're going to have x1 to the 4th, x1 cubed, x2, x1 squared, x2 squared, x1, x2 cubed, and x2 to the 4th. Okay, so you're going to have 5 additional terms. Okay, 5 in addition to the original 9. Okay, plus the 1 gives us a dVC tilde of 15. Okay, and you can keep going. Okay, and by the way, this polynomial transform exists for an original input dimension of also d. Okay, so it's the same idea. You take, the augmented 1, then you take the linear terms, then all quadratics, then all cubics, and so on. Okay, so we could define phi q, okay, is the polynomial transform of degree q. It's an interesting counting argument to ask. If you're in d dimensions of degree 2 for an original x of degree d dimensions. Okay, you can ask, okay, so this transforms into what dimension? And it's an interesting counting argument. You can go and show that the dimension of the space is going to be Q plus D, choose Q. Okay, so it's very rapidly growing with Q, okay, especially if D is large. So that the dimension of the space is that minus 1. So this is D tilde is equal to this, and dVc tilde for a Qth order polynomial transform in D dimensions is going to equal just Q plus D, choose Q. So it's an interesting counting argument. I challenge you to go and figure that out. Okay, the point is that as you increase the VC dimension, as you increase the order of the polynomial transform, especially when the original dimension D is large, okay, you're going to get an astronomically large dVc, and you will lose control of E in versus E out. Okay. Now in 2 dimensions it's just growing quadratically. It's not as bad. Okay. In D dimensions it's growing polynomial in D, Q to the D. Okay. Now, so what's my recommendation? So you think about your problem, okay, and if you think that you need a little bit more flexibility, well then I would suggest go to the quadratic nonlinear feature transform, the degree 2 polynomial transform. Okay, if you really want more flexibility, go to the 3rd order polynomial. Now let's go back to the problem that we had at the beginning there, and let me show you. Okay, so if I went into the polynomial transform, it was kind of magical that I said, let me ignore this, and that, right? I said, earlier I said, let's go from, x, x1, x2, I said, let's go to 1, x1, z1, z2, which is equal to x1 squared equal to x2 squared. Now that was just for illustration, but how did I know to ignore the linear terms and to ignore the cross term in the quadratic? You would never know that, okay? So you just need to make the decision, I need to go to the 2nd order polynomial. Linear is not good enough. Okay, so if I go to the 2nd order polynomial, then I must use the full 2nd order polynomial because I'm not allowed to look at the data, and then that's what we get, okay? And it's quite nice. It's an ellipse. Generally it's an ellipse, and I've gone into this 2nd order polynomial space. And, that's a reasonable fit to the original data. Okay. But, important, under the hood, behind the curtain, okay, behind closed doors, the client doesn't know. But all you're really doing is using the linear model in this, more complex space. Okay. Now, I just want to show you that, we have here in the polynomial nonlinear feature transform, we have here a real monster. So you have to be careful, okay, when you use this polynomial feature transform. And let me illustrate with this example. Okay, so here's remember I showed you earlier 2 cases of non-separability, and this is the one where we said, well, here it looks like linear, so let me tolerate the error and use pocket, and I'll get 2 errors, E in of 2 or 2 over n, and my E out will be nice and tightly linked to E in. So you might think, well, I'm not happy with that. And I learned about this tool called the nonlinear feature transform, and I'm a strong computer scientist. I can handle lots of computation. So let me use the 4th order polynomial transform. Okay, so let me show you what happened. Well, now having learned the theory, we know that you're going to have to pay the price in dVc for this small number of data points. Okay, and sure enough, when you go to this 4th order polynomial space and fit and then, do the inversion and see what does the decision boundary look like in your original space, look at that. Okay. Perfectly fits the data. So E in equals 0. No doubt. Okay. E in equals 0. Okay. But so what? You've lost control of E in versus E out. And that's what that shows. Now you don't need fancy complicated VC theory and all that to look on the right picture and say, that's not going to perform well in practice. It looks like, have you overfit the data? So I'm throwing some language at you that we will learn about later. But, you don't need sophisticated theory to look at that right guy and say something is wrong. What is wrong is that you don't expect that guy to perform well in practice. And the theory says that as well, but has a very, very quantifiable, precise reason for why. You've gone into a huge dimensional space, and you've lost control between E in and E out. E out is no longer equal to E in. You don't expect that guy to do well in practice. Okay. So, on the left is our sports car, the linear model. Okay. Think and use it think because you need to construct the right features, and then use it because it gives you the link to E out. Okay? And if you can get E in small with the linear model, you've solved your problem. You have succeeded. Okay? If you think of the linear model as a sports car, the nonlinear transform that you put on top of this linear model is like a monster truck. It's like a truck. It's like an 18-wheeler. Okay? It's a huge monster. Okay? And with that monster comes a lot of momentum. And that momentum is very hard to stop. And as you can see, it's just going to go ahead and eat up all the data and fit it all perfectly. Okay? And you need to be very careful before you decide to go to the high order polynomial transform. Okay? It's very hard to break that guy. It's very hard to rein it in, and it goes and does that wild stuff. Now, you might wonder, is it possible to get this monster power of the nonlinear model, okay, but still not succumb to that, weird classifier that pops up that albeit fits the data, but I don't expect it to generalize? Is it possible? Well, so can you, have your cake and eat it as well? Can you have the power and not fall into that quote-unquote overfitting trap? Okay, now overfitting, we haven't studied this thing. It's language that we're going to see later on. Advertising. Okay, we'll have to deal with issues like that because you have picked your polynomial transform before you look at the data. Okay, so what if you picked it wrong? Can we still survive? Okay, then we need more sophisticated tools. We'll study that later. Okay, for the moment, I just want to end by showing you the digits data, okay, and making a plug, okay, giving you an advertisement. Okay, so if you look on the left, we see the linear model. Okay. And it does pretty well, but it gets a in-sample error of about 2.3, 2.4%. Okay, and then the out-of-sample error is comparable. Why? Because it's the linear model in 2 dimensions. We've got a tight link between E in and E out. On the right, okay, what happens if you go to the third order polynomial? Well, you get a much nicer looking fit. Okay, but that's fine. That's good. Okay, much nicer looking fit. And because you have enough data, you still have control between E in and E out. Okay? And you improve the performance by, maybe 1%. Okay. And, and because there's enough data, that percent translates into out-of-sample performance. So E out is close to E in. So when you have more data, you can afford to be a little bit bolder and maybe go to the third order polynomial. It gives you that little bit of extra flexibility to get E in small. Okay. And then you're wondering, wow, we did all this work. We've done like 6 weeks or whatever, 4 weeks of this course, 6 weeks of this course, and, we just got a 1% improvement in the error? So what that means is that, my accuracy went up from something like 97.5%, okay, to 98.5%. Big deal! Okay, I did all this, mechanics of the nonlinear transform and this and that and choosing features and all I got from going to the nonlinear transform is 1%, a mere 1%. 97.5% goes up to 98 or plus change. Is it worth it? And that's the nature of machine learning. Okay. And in general, solving problems like this, you can very quickly, with simple models, just intensity and symmetry, and the linear model, you can very quickly get very decent performance. And that's what I meant by if you cannot more or less solve your problem with a linear model, you probably didn't understand the problem. So you can very quickly get decent performance, with not that much effort. Okay. And then the expert comes along and puts this, these finishing touches, okay, to get you that extra percent. Okay. And given that you're already pretty high, there's not much room to improve, but that extra percent, it's sort of a diminishing returns. You put all this extra work, you get an extra percent, but that extra percent is worth it. Okay? Because if you think that, there are 300 million people, and if on average they send a piece of mail every day, let's say a piece of mail every week, or, all that junk mail that's coming, it has to be sorted. So you have to read digits. Okay? And there are 5 digits in the zip code. So, 300 million pieces of mail a day times 5 digits. Okay. That's, 1.5 billion. That's 1.5 billion pieces of mail a day. That 1% improvement, okay, makes sure that a lot of mail doesn't get lost. Okay. So this small improvement is worth it when you're dealing with big numbers. And that's the nature of the game, is that you get up here and then you put a lot of effort to make small improvements. Okay, and those small improvements are where all the real money is. Okay, think about credit approval. So you've got your people, and you've got your clear approved. Okay, you've got your clear approvals, and you've got your clear rejects. Okay, and now you've got your borderline guys. Oh, these are X's. Sorry. Okay, and now you've got your borderline guys. These guys. Okay. And these guys. Okay. And all the money is made in the borderline, believe it or not. Okay. Because the clear rejects, no problem. Anyone and their mothers are going to reject. And the clear accepts, no problem. Anyone and their mothers are going to accept. And you don't make money off those guys. Because if they're going to pay off their loan, okay, good. They paid off their loan. They're not going to get a loan, so I don't make or lose money. But this borderline are the guys who pay off lots of interest and so on and so forth. So getting that extra % of accuracy back from the linear model, which would do this, if you can do the nonlinear model and do that, okay, you get these borderline guys who are going to pay off a lot of interest, and those non-borderline guys you reject who are going to lose you money. And now that's where the money is to be made. So that 1%, don't laugh at that extra 1%. Okay, that's all I'm saying.